Okay, welcome back, everybody. So we are going to continue. An important point is that all of these that I've shown you, these families of atomic types, they are actually completely agnostic of the technology. You can look at any technology, XML schema, JSON schema, Java, Python, and so on. It's always the same families of types. Now they might have different names, right? For example, I told you float in Python is actually double in Java and so on. So the names might actually differ. But after all, it's like Swiss German, right? Who is Swiss German, right? So who says Fenster, Feister, Fenster, like Fenster? Yeah. And there's then Obig, Abend, Aber, Ober, Obert, like all these ways of saying the same. And we all understand each other. It's exactly the same thing in here, right? So we have all of these types. They might have different names, but that's okay. They are the same, right? So it's just a matter of looking up the documentation, and then you know how they are called. So one more thing about the atomic types.
Maybe shortly, there was a question on Zoom.
Yeah.
So the user asked whether it's a good idea to use long to store the epoch millis in order to get rid of time zone issues and mitigate the 2038 problem.
Yep, that's a very, very good point. So thank you for this. It is indeed recommended, for the integers. So that's, I showed you on the numbers. Ints nowadays, well, I told you about the Gangnam Style video. It's not a good idea anymore to use this. So now the default should be long if you want to be absolutely sure that nothing's going to break. That's also true. So internally, the dates can also be stored as longs because you mentioned the 2038 bug. But this is an internal representation. Logically, a date would be stored like this, and then the long would be an internal detail of the representation of the date, right? But you're absolutely correct that it's a good idea to use long instead of int, so the 64-bit representation, the one that goes to 16 quintillion. Okay? I have to be careful not to go too fast because it flickers a little bit if I click too fast. So the next thing I wanted to show you, it's a bit of a theoretical detail, but it's an important detail. When we validate data against types, remember that data is originally text. So it means that when you have, let's say, an integer that you validate, in the XML or JSON file, that integer is in text. So it means that, for example, you might have, let's say, 42 that you intend to validate as an integer. But in the original JSON, it's going to be the character 4 and the character 2, right? Text 4 and 2. These 4 and 2, so the textual representation, is called the lexical value, right? Or a literal. It's an integer literal. That's how you write it in base 10. You could also have other conventions like the scientific notation, plus 4 is 0, 4 times 10 to the power of 0, that you could also find in JSON, right? So I'm not sure if it would allow the plus, even though some might, but you can have scientific notation. Do you agree 4 or 4 is 0 is the same number? Once you've validated it, it's 4, right? And so when you have validated it and you have the actual 4, then you are looking at the actual value. So this is the typed value, the mathematical concept of 4, like 4 oranges, like a cardinality, right? So do not confuse the lexical representation or the literal, which is how it's written as text, and it can be in many different ways for the same value. Do not confuse it with the typed value that is what you have in memory and on the logical level after you have parsed and validated. For whom is that clear? Right? Very good. Here's another example. Dates. This is how you would have them in JSON or in XML. That's 1st of August, 2017. That's the ISO 8601 standard that says it's 4 digits for the year, then a dash, then 4 digits for the month, then the dash, and 4 digits for the day. So that's a standard. And that is text, 2017-08-01. That's a lexical value, a literal. And then you convert it into a typed value here that is in the value space, which may or may not be internally be a long, like Excel does, for example, but the user doesn't care because the user should see the dates, right? Okay, so that's another example of lexical space versus value space. So the lexical value versus the logical typed value. And here's another one with a timestamp. That's also the ISO 8601 standard with year, month, day, hour, minute, second. Z is for the UTC time zone. And that means this typed date. And that would be the textual representation of the date time. Here's another one that's not a Star Wars robot, P1Y2MT3H. That's actually lexical space. It's also the ISO 8601 standard that says 1 year, 2 months, and 3 hours. The T here is the same T that you have to separate the day from the hours, right? It's also the same T. And P is just always P. It's always that letter. Just tells you this is a duration lexical representation. And of course, on the right is what you would see in XML or JSON in the actual text document. But once you have validated it against duration type, you have the logical 1 year, 2 months, 3 hours value, which again may or may not be stored as a long in the background, but that would not be part of the logical value. All right. That's it. Yes? So here, what's very important, you were asking about the efficiency in terms of the storage, the space that it takes in memory. So there are several things. First, by virtue of data independence, when I'm on the left, I don't care about the storage size because anybody can do anything they want, right? If I give you that date on the left, it's entirely open how you want to store it. It's up to the engine or the database engine how he wants to store it in memory. This is just what the user sees, right? It is only what the user sees. But in the memory, the implementation can optimize that. There are even implementations, let's say, that expose the entire integer space, like without any limits, but that automatically are able to see when it's a small integer and fall back to an int or even a short, right? So they are able to do that. And so it's something that data independence gives you, because then you can do whatever you want in the background. You can optimize in any way you want. The second thing is that it is indeed one of the virtues of this conversion that's a nice example. In the XML document, that would take a lot of space because this is a sequence of characters. It's 2014-12 and so on. If you're optimistic and say, okay, this is 8 bits per character, this is 1, 2, 3, 4, 5, 6, 7. So that, let's say 20 times, that's already 160 bits, right? That's very, very long. But if you have parsed this with a validation engine, and now you have this representation, in the background, in the memory, you can just model that as a long, like the number of milliseconds since January 1st, 1970, for example. But that is an internal memory representation, and that memory representation is going to take less space than the original lexical representation, right? So we're actually compressing and optimizing the space. Now, which is also related to your question, maybe you meant, isn't XML and JSON a waste of space, right? You could also, it's fair to ask this question, right? And what I will show you at the end of this lecture is that indeed, XML and JSON takes more space. And in fact, once you want to validate, you have validated an XML, a bunch of XML documents or JSON documents, there are other more efficient binary formats to do that. So you can save it again as Parquet, for example, which is another format. And Parquet is going to be much, much, much smaller than the JSON file, right? So it's a great idea to actually do that and save storage space. And also because when you read it, it's going to be faster. But two things. First, you can only do that when the data is valid. If the data is not valid, then you can't. And so this is where JSON and XML are actually useful because you just store it as text. You don't have the constraints that the data must be valid. The second thing is the long-term durability of the storage. And when I say long-term, I just don't mean a few years or a century. I mean like 1,000 years, 1,000,000 years. This is something that there are people researching that, but there is this worry that archaeologists in 1,000,000 years might notice that starting from, let's say, the 2000s, there is nothing. There is absolutely nothing. There's no paper. There is absolutely nothing printed because everything was digital, but nobody can read it again. It's all lost, or the drives and the CDs are long gone. And so there is this worry that our descendants will have nothing to find out about us. And so there's the notion of how do we archive or make sure that some of the things we do can be preserved in the very long term. And this is something actually very concrete because like if you look at the ETH library, they have a so-called research collection and you can put data in there. But the data you put in there, you cannot put anything. And typically they will ask you to have specific formats that we believe in the future people will read, people will be able to read. And so what we like is formats like text formats, CSV, XML, JSON. This is something people can read. But as soon as you have a binary format like Parquet, for example, how can we know that in a century, people will still have the drivers and the libraries to read that file anymore, right? So this is also part of the thinking that even though it takes more space, textual formats like XML, CSV, JSON are actually useful for the very, very long-term preservation of the data. Does it make sense? And did I answer your question? Awesome. Okay.
So we have another question on Zoom.
Mm-hmm.
A user asked whether it's correct that validation converts value spaces to lexical spaces.
The opposite. But more exactly, it would be the annotation that does that. So strictly speaking, validation is yes, no. You just say yes, no. It's valid, it's not valid. And so what validation will do is that it's going to look at the lexical space and tell you, yes, this is a date time, or no, this is not a date time. That's what we call validation. Converting the lexical value to a value in memory would be called annotation, right? And you typically do annotation at the same time you do validation. They go hand in hand. Now, it's not incorrect to say validation because there's a lot of people who actually do use validation for annotation. So there are people who would say that it's also part of validation that you convert the lexical value to the typed value. So it's more a matter of how strictly do you use the word validation. So to give you the vocabulary, converting to the lexical space requires parsing plus validating, annotating, and that gives you this value in here. The other way around, which I think this is what you ask on Zoom, how do you create out of this value, you create the lexical value that has a different name. That is called serialization. That's when you have executed a query, you have output values, and now you want to store them again as XML or JSON to send it to other people. Then this is called serialization, right? So right to left parsing, validation, annotation, and left to right, serialization. Is everybody with me? Yep. Okay. All right. And just so you know, you probably know from Python and Java, we can have subtype, for example. Decimals are a supertype of integer, because all integers are decimals, but not all decimals are integers, right? So you have this concept of supertype and subtype also in many of the systems, but this is already advanced. I mean, not everybody uses these things. All right, so that was the atomic types. Strings, numbers, dates, date times, binary, durations, and so on and so on. More or less all the same everywhere. So let's go to the structured types now. The structured types, I also have good news for you. It's pretty much the same everywhere. Not the same names, but still the same. So, for example, in JSON, we have objects and arrays. We'll get back to the sun right after that slide. The name for an object, the fancy theoretical computer scientists call this a map. That's an abstract data type that basically is a JSON object. And the arrays, the theoretical computer scientists would say it's a list, right? I think even in Python, it's called a list explicitly. In Python, this is called a dict or dictionary. Now, if you look at XML, XML elements can also be viewed as lists because you have the children of an element would be an ordered list, right? The order is important. You can even repeat the elements as children. And a set of XML attributes would again be a map where the attribute names would be the keys and the attribute values would be the values, right? We'll see data frames at the end of that lecture, maybe next week. A struct in a data frame would be also a map like a JSON object, and an array in a data frame would be a list. Who has already touched data frames? Some of you, right? You will have an insight how data frames relate to JSON at the end of this lecture. Should I do something about the slides or is it good for you? Can you see? It's still okay, right? Okay, if at some point the sun starts preventing you from reading, then we will fix it. Okay. All right, so what I'm saying is that no matter what technology you use, there will be some concept of JSON object and some concept of JSON array, or that looks pretty much like it, right? In many of the systems, we also have the concept of cardinality in one way or the other. For example, you might have, so this is, for example, from Google's protocol buffers. Required means that it's one value and it has to be there. Optional means that it can be there or not there. Repeated means you can have many repetitions of that kind of value. The symbols that go with it are very often for an optional, when there's a symbol, it's often the question mark. When it's repeated, it's often the star. And for required, we, like in JSON-X query, we don't put anything. So the default is exactly one. And plus is when it's repeated, but it cannot be zero. Then it's one or more. And you see, 1, 0 or more, or the star repeated, 0 or 1, or the question mark or optional, 1 or more, or the plus, doesn't have a keyword in protocol buffers. So what I'm saying here is these concepts are the same everywhere. Who has already seen regular expressions somewhere, regexps? It's the same symbols, right? That shouldn't surprise you. The plus, the star, the question mark, they're used exactly in the same way. Very standard. So what that means is that now if you start learning any technology and you see either these symbols or these keywords and so on, you will not be surprised, right? You see how this maps between the technologies. So these are called cardinality or cardinality indicators, right? For example, for the contents of a JSON array, you could say a JSON array has to be exactly one element, or it has to be 0 or more elements, or it has to be 1 or more elements, right? So that's, for example, for validating a JSON array. Okay. Now I did this slide. Don't be scared. It was one of you who requested it from a previous year. They wanted to see a beautiful mapping of many different languages and how they map to each other. And so I did that. It's not with the purpose that you learn that by heart or anything, but I just wanted to see. So this is a little bit like Zurich-Deutsch, Basel-Deutsch, Ostschweizerdeutsch, Bern-Deutsch, Westschweizerdeutsch, let's call it this way, and you know. So these are all the correspondences, right? So you see, for example, I told you double in Java also, in XML, JSON is called double. In Java, in JSON, it's just a generic number. Double, that's Java actually. In Spark SQL, it's going to be in Java. PostgreSQL calls it double precision, and Python is the only one that calls it float, right? But we just know it's the same. It's basically the same. And you can do for any type, you have this correspondence between JSON-ic and JSON, that is for pedagogical purposes, JSON schema, XML schema, Spark SQL, which we'll look at in a couple of weeks, PostgreSQL, some of you saw it in information systems, and Python, which many people actually know. Okay, I have to do something about the sun now. Let's see. Let me close that again. All right. Right, so this is the meaning of this slide is exactly this, to tell you, even though the names are different, it's always over and over and over and over again, the same families of types on the high level. So now you can learn maybe in 1 year, you will work for a company that uses a different technology. No problem. You can just look at the documentation and you will not be surprised. It's going to be exactly or more or less the same types all over again. Who is with me? Right? Okay. By the way, dict list, as I told you in Python, dict and list corresponds to object and array in JSON. Okay, so now that we have covered the types in a very generic way that would apply to pretty much any technology, we'll now start validating JSON or XML. I will start with JSON because it's a bit easier, and then I'll go to XML. I'll teach you 2 technologies in JSON. The first one, JSounds, is for teaching purposes or pedagogical purposes because it's easy to learn and it matches the pattern of the JSON. And JSON schema, which is in widespread use, right? And then you can even compare the two, and that should allow you to learn the concept. And again, you will see that they all work. All the technologies are good, and it depends on the context and the company that you're working for. So JSounds. All right, so JSON we co-designed with a couple of colleagues for the purpose of having a simple schema language that makes it easy to learn and to teach, right? So now on many slides that follow, I'm going to split it into 2 parts, the upper part and the lower part. The upper part has the JSON or XML documents that I want to validate. So it's well-formed, it will be well-formed, and I want to validate it. In the lower part, I'm going to have the schema. Right? So the document we want to validate and the schema that we want to validate this against, right? This document, when we want to validate it, we also call it an instance. It's an instance, and we want to validate the instance against the schema. That's the vocabulary that people use. Now, does anybody notice something about the schema? Something obvious, yes? Yes, absolutely, it has the same key, but even simpler than that, the first thing you notice, because you use the word key, is that it's JSON, right? So the schema is JSON. It's also a JSON document. And this is true in general. A JSON schema, so this is JSound, a JSON schema is also a JSON document, and we'll see that an XML schema is also an XML document. It doesn't have to be, right? There are other technologies, like for example, in protocol buffers, the schemas use a totally different language for specifying the protocol buffer schema, right? So it doesn't have to be. But it's very common for the JSON community and the XML community to just reuse the same syntax. So indeed, a schema for JSON validation will be itself expressed in JSON very often, and a schema for XML validation will also be expressed in XML very often. So that's the reason why you see 2 JSON documents, right? But just keep in mind, it's the one above we want to validate, the one below is the schema. Now your second observation is also correct, and that's actually a feature of JSounds, that it's meant to be this way, is that they look alike. They look very much alike. The only difference is that here you have the actual value in your instance. Here you have a type, string. Moreover, that type is taken from here. You can have, there's many more actually. It's not everything, but this is from this column, any of these types. So you put here, and it means this is accepting an object such that if it has any key called last, then the value must be a string. Is this document valid against that schema? Yes, right? It is valid because this is a string, right? It can be at least turned into a string. Doesn't have to be a string, but it can be turned into a string, right? So this is indeed valid. Now, most of the examples that I'm sharing with you, you can actually play with them on that address here. So this is the public RumbleDB server. The same one, if you do who did the JSONic tutorials? Some of you, right? It's RumbleDB. We'll have a week dedicated to teaching. I'm just giving them to you in advance because it was a request in previous semesters to take it slowly. So that's why I'm giving them a bit in advance. So this is a public RumbleDB server that is running on very small machines, I think probably 2 cores and 1 GB of memory, so super, super small. It's only meant as a public service for people to play with. And so if you go to that page, you will have one big text box for putting the instance and one big text box for putting the schema, and then you click on a button, and then it tells you it's valid, it's not valid, right? So this is in case you want to play with it. Okay, but coming back to another example, always my instance on the top and my schema in the lower part. Who agrees that the instance is valid against the schema? Yes, I see a lot of nodding. Yes, it is. Last must be a string. It is a string. First must be a string. It is a string. So it is indeed valid against my schema. Now, by default, everything is optional, meaning that if you have in your schema first must be a string, but it's not there, you see in that instance there is no key called first, that's okay, because it's optional by default, right? Now, the schema languages might vary. Some schema languages might say required is the default. Some others might say optional is the default. It doesn't really matter, right? You just look at the documentation. But in the case of JSONs, it's optional by default. Okay. What do we have next? What if you want to make it required? What if you want to say it has to be there? Last has to be there, and first has to be there. In JSON, that's the compact version of JSON, you put an exclamation mark in front of the key. So exclamation mark last means it's required, and you agree that the document above is valid, right? But this document here wouldn't be valid against that schema, right? Because the first would be missing, right? So we use an exclamation mark. Then we have numbers. For example, I told you you can use any type from the left column on my overview slide. Now we have h that must be an integer. Is it an integer? Yes, 142, right? 142. So the h is an integer, and that is valid. Who agrees the instance is valid against the schema? Yeah, awesome. And together with validation, if we also have annotation, then this 142 will be converted in memory to a long or an int or a short or even a byte, because it's a very small one. Okay? Now, it turns out that when you validate, you could have quotes that would still successfully validate. You could have quotes 142 quote, it still matches with an integer. All that matters is the lexical value. Doesn't matter if it's quoted or not. Is that lexical value that of an integer? Yes. It doesn't matter if it's quoted or not. Right. Okay. And likewise, this would also validate as a string. If I say h string, that would also validate. It's just that that would be then the string 142, and in memory, it would be represented as the string 142. Right. For the purpose of validation in JSON, it doesn't matter if you're quoted or unquoted. It always looks at the literal, at the lexical value. Okay, now we have Booleans. Is that valid? Yes, absolutely. Physicist is expected a Boolean. Is that a Boolean? Yes, TRUE. That's the lexical value of a Boolean. So yes, this is valid. Then we have a special type called null that has only one value that is null. And so location has to be null. So yes, it is valid as well, right? Who is with me? Everybody, right? Okay. Now, I told you it's the left column of my overview. Here's a complete list. Well, almost complete. You see that's a very, very long list. Look at all these numbers, right? This all comes from the XML schema standard, which is shared with JSON. Positive integer, negative integer, non-negative integer, non-positive integer, unsigned long, unsigned int, and so on and so on. So all these representations, right?
Sorry, there's a question for your comment before.
Mm-hmm.
The question is, can also a string be without quotation marks?
Yes, if it is true, false, null, or an integer, yes. But that's because it has to be well-formed. If you would have a string that is not a number or a true, false, null, then it would not even be well-formed. So you have to remember that whatever you want to validate is well-formed in any case. right? But once it is well formed, then you just ignore the quotes for the validation. Yes? Yes, absolutely. Many schema languages allow you to do that. So JSON does, JSON schema does, XML schema does. You can absolutely specify that. In fact, you're creating your own subtypes when you do that, because the integers that are lower than 100, it's a subtype of the integer of the int space, right? And yes, you can do that. You can specify, for example, I don't know, a control shielder of a car. That has to be exactly, a content with 2 letters and so on. You can also restrict that. A content with 2 letters, like all of this you can do in a schema. You can specify the length of a string, the interval of an integer, and so on. And very often you even have a way to even write your own script that says yes or no. You can even program what you want to test. Yeah. Yes, but that would be the verbose syntax. So JSON has a compact syntax and a verbose syntax. I'm teaching you the compact syntax because this is the one that is easy to learn. So in the compact syntax, you could not do it. But in the verbose syntax, you would indeed have an object where you specify an upper bound or a lower bound as a key in an object in your schema. Yeah, that's actually how it's done. I just don't want to overcomplicate, when I show you how it's done. But the answer to your question is yes, it can be done in the verbose syntax. Yep. Did I answer your question? Yep, awesome. Okay, so that's the menu. You see a very large menu of types to pick from, and you can put any of these inside the, as a type, basically. Now, there is also, in all schema languages, a notion of the type that accepts anything, right? That anything is valid against it. In JSON, it's called item. And you have that in, I think in JSON schema, I will show you there's a way to do that. But basically, when you say location item, it's a way of saying whatever I don't care, right? Location can be whatever you want. So this is it. And it turns out here to be an array of strings, but since I said item, it can be anything, right? So now, of course, when you do a schema like that, it's a bit lenient, right? You don't force things too much. You just say that can be anything. But you can also be a bit more specific. And instead of saying location is whatever, you can say that R, in that case, is an array of whatever. It has to be an array, but what is in the array can be whatever, right? So an array of items. Do you agree here we have an array of items, right? So the instance is valid against the schema. Who sees that? Right? It's an array of items. And you see the compact syntax is meant to be legible by a human being. Here, we say it must be an array of integers. Also, very compact syntax. And you agree the instance is an array of integer. It's an object with R, ARR, associated with an array of integers. Right? Who finds it easy to understand? Right? It's very, very straightforward. So that's the goal of this syntax, is that when you look at the schema, it always almost looks like the instance in some way. So it has the pattern of the instance. Okay.
There's another question.
Yes?
So the question is, can item be replaced by multiple values?
That would be a union then. So again, that would be with the verbose syntax. With the verbose syntax, you can create union types. And you can have the union of integers and booleans, for example. And then you can have an array of this, an array of the union of integers and booleans. And that gives you an array of integers and booleans. Does it answer your question?
They were referring to the last example. So if you have an array of items, can item be replaced by multiple values?
Oh, no, just one. It's just whatever type you want in your array. Here it has to be just one type, the type of each member. Did that answer your question? I'll come to you after that.
So they say you have an array of items, then we have multiple items, but there we have, so I guess it's, you have only one item in the JSON, in the schema, but then you have multiple values with different types in the instance. Basically, so I guess the question asks whether this is possible.
So let me say several things. So first, in the compact syntax, you put one type here, and that type has to apply to every value in the array, right? So that's the compact syntax. Now, perhaps somebody would like to say, I want an array so that the first value is an integer, and the second one is a string, and the third one is null, and so on. You can also do that, but that would be, again, with a verbose syntax and maybe with a script, with your own script, right? So yes, in principle, you can do that. You can also have a length of the array that's also with a verbose syntax. You can say, I want items, but between 2 and 8, for example. And that you would also do with a verbose syntax. As soon, basically, as it's an advanced feature, that would be with the verbose syntax. The compact syntax is meant to cover 80% of the use cases, the ones that are simple. Yeah. Did I answer your question on Zoom?
They say, okay, so with compact we can.
Sorry?
I think it answered the question, yes.
Okay, awesome. And otherwise, we can continue offline, right? You can send us a message. Yes? Oh, I already answered. Awesome, perfect. Very glad. Any other questions? Okay. Very good. Now, here are the superpowers. You see the simplicity of the language. Now I have an array of objects that have a key foo associated with a Boolean. That's my schema. R is an array of objects with a key foo associated with a Boolean. Right. So again, the goal is to have the pattern in here. That gives me a valid instance. Here's another one with extra fields. So the idea is that when I have a schema like this in the compact form, every key is optional. What you cannot have is extra keys. So that instance is valid because it only has last and first and nothing else. Now, some people want to allow extra fields, right? Maybe you want birth date and so on. It's not in the schema, but maybe you would like to allow your instance to have more keys that you have not anticipated in the schema. So that you can do too, again, with the verbose syntax. But now I've talked so much about the verbose syntax that maybe I can show you what it looks like, but I'm not going into the details of that. This is not part of the material, it's just for you to see. Because obviously the verbose syntax is verbose, right? So it's going to be more complex. That's what it looks like. If you go to the verbose syntax, that's the same thing. That's the compact form, and that is the verbose form. And so when it's expert mode, basically. So when I am in expert mode of the verbose JSON syntax, I can add here a property to my schema that says closed false. Closed means I don't accept any other keys. If I say closed false, then it's open. And if it's open, now I have year 1905. It's not in the schema, right? Year is not in my schema. But since now I'm saying it's no longer closed, it's open. So any key that is not in my list is fine, and it can have whatever value it wants, right? So in the compact syntax, it's not allowed, but you can, in the verbose syntax, extend it a little bit. You're not expected to know the verbose syntax, right? Just to be clear, just so that you see it's a bit more scary than the compact syntax. Okay. So as a conclusion of JSounds, I want to recap on the sort of things that we can do in a schema language. First, you can restrict values to a specific type. You can say, here, I want an integer, or here, I want a date, or here, I want an array of whatever, right? So you can restrict specific types. Second, it's then annotation. You can implicitly cast. Who heard of the word cast? Who never heard the word cast? Who heard of the word cast? I thought 3-valued logic in the lecture hall. All right. So indeed, when you have the JSON foo2134 and you expect this to be an integer, that's going to implicitly cast it to an integer in memory. You're going to have a representation of the integer, right? So it's as if it would be unquoted, right? You would remove the quotes. But that's only an approximation because in fact, it's going to be in memory. It's no longer the JSON syntax at that point. It's a memory tree representation of what you had. The next thing you can do is require a value. You can say, I want this key to be here, the exclamation mark, right? So you can require the value or you can make it optional. It's your choice. The fourth thing you can do is allow or not for extra keys. That's open or closed. You can open your object type or you can close your object type and allow or forbid additional keys, right? That's also something that is in your control. You can choose to do it or not to do it. There's also advanced things that I'm not getting too much into, but you also have the notion of default value in a schema. It's possible to say, if some field is not specified, then in the memory, add that default value. For example, you could have a database of addresses, and if the country is not specified, then you consider the country is Switzerland, right? And that means that it's not in the instance. You didn't have country Switzerland, but once it's in the memory, you add, as part of the validation and annotation, you add country Switzerland. If it's not there, if it's there, then you take it. That's the default value. Yeah. And then you can also support primary keys. For example, if you have an array of objects, you could say foo is a primary key. So you could say, for example, you don't want any repetition. Here, that would be invalid because we have twice the same value, even though foo is supposed to be a primary key. I'm not showing you how to do it, but it's possible to do that, right? So these are the sort of things we can do with a schema. And this is true not just for JSON or for JSON schema. This is true in any schema language. You can do that sort of things. And even in XML or XML schemas, right? So now, here's a real life example. This is the great language game. We love to use it in the exercises of that lecture. We have a data set with 2 gigabytes of objects that look like this, 16 million of them. This was based on a game a couple of years ago where people would listen to a sample of a spoken language and they would have to guess, is it Maori, is it Mandarin, is it Norwegian, or is it Tongan? And here you have the correct answer, and here the answer that the user gave, which here was correct. It was somebody who played from Australia on that date, and that's just an identifier for the sample. Now, it turns out that this is the structure of the entire data set, so you can have a schema for that, and that's what the schema looks like. Guess is a string, target is a string, country is a string, choices is an array of strings, sample is a binary, hex for hexadecimal, base 16, and the date is a date. So you see, this here has the pattern of that instance. So in JSON, it's very straightforward to do, right? Who agrees with that schema for this instance? Awesome. So this is real life. And here for this document right here, who would be able to do the JSON schema for that? Most of you? Is it what you had in mind? More or less, right? So of course I put long, I could have put int or integer or whatever in here, but that's the idea, right? So you see A, integer, B, Boolean, C is an array of objects with foo and bar. Foo is required, exclamation mark. Bar is optional because it's not in here. So bar and array of longs, right? So this is the idea. So you can very easily build a schema out of an example instance. Okay. And so I'm stopping here for today with the JSON. It's made for teaching. Next week, I will show you JSON schema. But now you already know one language. You will see it's easy. It's just a different language, different conventions. But you will see it does exactly the same thing. All right. So thank you very much, everybody, for attending so early with summertime. Thank you, Florian, for moderating this lecture. Enjoy the exercises. And I will see you next week for the continuation of this lecture. Thank you very much. Have a good day.